Alright, hey guys, what's going on? So today we are going to be talking about activation functions within the context of artificial intelligence. And so without further ado, make sure to hit that like and subscribe button. You can also go into my Patreon page to support the channel, and you can become a member here as well to support the channel. I intend for this playlist to be very vast and expansive. We're going to go over a lot of very interesting concepts in artificial intelligence, and we're going to learn how to build artificial intelligence from the ground up as well. We're going to be able to understand as much as we can when it comes to machine learning, artificial intelligence, and so forth. And in this particular playlist, we're going to be looking at AI, okay? And we really want to understand it from the ground up. What I'm doing in these first few videos is just laying out the theory of things, and then we're going to dive into the making computer algorithms and stuff like that with example data sets, okay? So with that being said, let's go ahead and get started. Again, make sure to hit the like and subscribe button, and become a member here on YouTube as well. Okay, so activation functions. What is an activation function? Well, put simply, activation functions are things that when we put, so in the last video we talked about placing weights on various different types of inputs. These inputs then are fed into the brain, right? The brain then applies something called an activation function, and that activation function is it sort of sets the threshold, if you will. When you think about biology, you have this thing called an axon hillock within the nerve cells. Those things act as thresholds, right? A certain amount of signal is going to come into come from the dendrites, right? That signal gets passed through the axon hillock, and the axon hillock is like a gate. It only opens when a certain amount of signal gets to the axon hillock, and if that signal surpasses some point, then the axon hillock is going to open the floodgates, if you will, and the information is going to propagate down the axon. So in a very similar way, that's how these activation functions are going to work. And so we have this function, right? We have this function here that acts as this thing that will take all the inputs, right? So we have taste, hearing, eyesight, smell, and touch. This is our 5-dimensional space, if you will. Each one of these has its own axis, Each axis is orthogonal to each other, and our weights might correspond to a particular set of input values that might look like this, right? So for our taste, we might have 1.5 as a value out in front. For our hearing, we might have a weight of 0.25. So whatever we're observing, if we can't hear it very well, the number in front of that thing is going to be 0.025. If we can see it relatively well, we could put a number like maybe 2.7 in front of the eyesight axis. We can have, if it smells really strong, right? So what's something that we can not hear very well, we could see relatively well, but its smell is very strong? Maybe a skunk, right? Skunk smells pretty bad. They don't really make a sound, but you can see them, right? So this might just be an example of a skunk, right? You can't really taste a skunk, though. That'd be kind of weird. But it's just some object, right? Some object. You can't really feel a skunk either. I feel if you got close enough to feel a skunk, that'd be bad news. But we can have the point here is that we can have numbers, just any arbitrary numbers, in front of these. Each dimension of perception, if you will, which and each weight corresponds to how much value is being placed on each domain of perception. The smell of this example has the highest weight on it, and so something that smells strong might contribute the most to the value of this function. So really low values we want to siphon out, because these values might only contain components attributed to the sound or feel of some object, okay? So we have these neurons in our brain, and that are looking at smell. Okay, they're really, really into just analyzing the smell of something. Okay, and so you smell something really strong, and those things are going to open the floodgates. Like, that's a lot of input. These nerve cells are thinking, okay, I'm looking for the smell, I'm looking for the smell. Okay, now I smell something really, really freaking strong. I'm going to open the floodgates. I'm going to start sending signals down, okay? And so to do this, to do this in a computer, you need this thing called an activation function. So the activation function, almost like an Axon Hillock, okay? If you don't know biology, it doesn't really matter that much. If you do, I'm drawing these analogies for you guys, okay? So there are four main types here. There are four main types of activation functions, but there's a lot more actually. But the four main types are threshold activation function. Right? So if all of this equals 0, okay, then none of this is going to get passed through. But if this equals 1, then it does. Okay. So it does, it gets passed through. Okay, so that's a threshold activation function. We have a sigmoid activation function. It's very similar to a threshold activation function, but it takes a different form, right? It's a continuous function. Okay, and so it gives some leeway for objects that might smell strong, but not super strong, but strong enough to get past the Axon Hillock a little bit, say, for example, when we're talking about this in biology terms. We have this thing called a rectifier activation function. Now this function looks like this, right? So anything past 0 this way is not going to get used, but anything that is 0 or greater, well, that gets put in as the actual value itself, right? So, and same thing here, right? It gets put in as the actual value itself, whereas here it's just 1 or 0. The output's just 1 or 0. So X could be 100 million. The output's just 1. Okay, it could be so the input could be really, really freaking strong, but the what gets passed in as the function is just the value 1. Okay. Whereas for the rectifier activation function and the sigmoid activation function and even the hyperbolic tangent function, 1 is not the only output, right? You actually get the number associated with the activation. So all of this is equal to some number, and that number is what gets placed into these ones. So this is not continuous. This is a discontinuous or discrete function. These other ones are continuous. All right. As an example, if we were to assume that our dependent variable is binary, we would use the threshold activation function, okay? Or we could use a sigmoid activation function if we were to treat the dependent variable as some sort of probability, maybe. Because again, probabilities look very much something like this, right? If X gets really big, for example, then this, whatever gets put into the denominator here, this looks like a probability almost, right? Because 1 plus something that is, this is going to be less than 1, right? Because of 1 divided by this, right? So the point here is that if our dependent variable is binary, we'll use this. If it's not, then the other 3 would be suitable. Okay, and we'll go through examples when we go through actual data. So let's take another visual example. And so in a simple neural network, we can imagine applying the rectifier activation function for our hidden layers, followed by a sigmoid activation function for our output node. So when we look here, our input layer these are our input layers, and then for our hidden layers, each one of these could have a rectifier activation function. So they're sending values. So this guy here could send a value of, say, 0.5. This guy here could send a value of 23.21. This guy here could send a value of 100,172. This guy here could send a value of 0.0008. Okay. Now, whatever comes in to here, okay, if that value is, I don't know, right here, well, that's going to get passed in as something that's very close to 1, okay, because 1 is right here. So that's just one example. This is to say that everything that has a value greater than 0 passes through the hidden layer nodes, and then we assign a close to binary value for each output and make that our prediction. Okay, so this could be something like, well, in our previous dog example, in our previous dog example, everything has ears, everything makes a noise, everything is furry, etc. And all of this information is going to pass as a potential dog, and then our output layer is going to make the determination of whether or not it's a dog or a cat or some lizard or something like that. This is not a very good network to predict dogs and cats, because we want our hidden layers to siphon out some things that are definitely cat-like qualities before the output layer makes the end decision. We don't want the output layer to be the only thing that is we don't want the output layer to be the only thing that's doing this activation function. We would like the hidden layer to do stuff like this too, not just be a rectifier activation function. So which is why we'll have a lot of hidden layers. Okay. So let's look at another example, but more geared towards a scientific question in drug discovery, because I want this to be mostly, this playlist to be mostly focused on how we can use AI in drug discovery, although every now and then we will talk about, we won't use examples in drug discovery, right? Because I want you guys, even if you're not into drug discovery or AI or anything like that, or drug discovery within the context of AI, I still want you to be able to understand this kind of stuff, and so we'll use examples that are not drug discovery related either. So, okay, so we have our input layer. Suppose each input layer then, I don't know why this is opaque, but suppose each input layer then contributes, say this one's going to contribute to looking at the size of some cell. This one is going to look at the age of some cell, and perhaps the way it does this is by looking at certain types of proteins that are expressed in cells as during the developmental process. And then suppose some of these also look at microscopy data, right? So we could take some confocal microscopy image, and we can determine the amount of yellow in the cell, right? So we have some yellow in here. We can determine the amount of blue in the cell. That's the nucleus when we look at typical microscopy data. And then we could also maybe look at the shapes of the cells as well, right? So the input layer, we have 5 input layers. Each one of them is looking at 5 different things about some sort of cell we're looking at and some microscopy data, okay? However, hidden layers then. So in reality, when we're doing artificial intelligence, when we're doing AI networking, or not networking, but when we're building AI models, each node is not going to be connected to every other node. What actually happens is that one of these hidden layers is going to take, say, for example, the size of the cell, the age of the cell, and the amount of blue in the cell, and say, well, I think the amount of blue is the number of capsaces, okay? So we can say, excuse me, we can say, well, okay, the capsaces, they get expressed as a function of the size of the cell. Perhaps if the cell is too small, they don't get expressed. As the cell ages, more capsaces get expressed, and as if there's a lot of blue in here, perhaps that's a signifier of the number of capsase proteins that are expressed in the cell. And so we say, well, okay, we'll take these 3, we'll send them to a node, and that node is going to say, well, I think that node is thinking, I think whatever input values I get from these 3 nodes, I'm going to assign that to, and then the amount of capsase molecules that I think are in this data. We can do another one, for example. We could say perhaps the size of the cell and the amount of yellow in the cell are linked in some way. We could have this hidden node thinking, well, I think the amount of yellow in the cell is the number of connexins, right? So connexins are proteins in cells that tether cells to each other. And as you could think, well, maybe if the cell is bigger, it has more connexins because it has more neighboring cells to connect to. Excuse me. And so what we get then is we have this thing assigning a rectifier with some number of capsaces and some number of connexins, okay? And then their outputs are going to get sent to an output layer, okay? This is my dog. He's a Great Pyrenees. His name is Reggie. And it is almost his dinner time, which is why he's begging right now. But I will finish this before I feed him. So this is how we think of activation functions, right? We have these things that are, we have these hidden layer cells, or these nodes within our hidden layer that are going to put a number on something that they think is correlated to each other, right? We can almost think of these things as inner products of, or because when we look at this thing here, this node is thinking, well, I think that there's a correlation between the size of the cell, the age of the cell, and the amount of blue in the cell. And I think, and based off of the data that's getting sent to me right now, I'm almost taking like an inner product between all three of these dimensions, and I'm going to compute an output, and that output is what I'm going to send to the output layer, okay? And then the output, it's going to be the job of the output layer to take in all the values that these hidden layers perceive, okay, and then make the final prediction, okay? And that is where we're going to start to get into the idea of the loss function and the cost function, okay? The cost function is what we're going to be talking about next. And the cost function is going to tell us something about what the difference is between the output layer and what the actual data set is telling us, right? So if this is data from someone who has melanoma, for example, and we have an output layer that predicts melanoma, then the cost function of this output layer is going to be 0. It accurately predicted, okay? If we'll say, okay, so say this is so say we have data from someone who has, I don't know, okay, melanoma, say this is data from someone who has melanoma, but the output layer says, I think this is someone who has some, I don't know, leukemia. Right. I think this is someone who has leukemia, and so the cost function there is going to be different. And it's going to be wrong, so we're going to have to update the weights on these things. And so that's what the activation function looks like. And with that being said, I will see you guys in the next video.